Now that we've introduced exponential functions, today you are going to work a little bit with some applications of exponential functions. You're going to think a little bit about exponential functions in real life. Before we dive into our notes for the day, I actually want to show you an example of an everyday situation that uses exponential functions. Several of you probably have savings accounts. So maybe you have your own savings account that you've been, putting allowance money or kind of side money into. Maybe your parents started an account for you when you were a baby. Maybe your family has a college savings account. So those are all investment accounts. So they all earn interest. So they pay out a percentage of interest each year. So the way we calculate, or the fast way to calculate the percent of a number, is to multiply the number. So to give you a quick example, let's say you start off with a $100 balance, and let's say that you make 5% on that each year. So basically what that means is that they pay you 5% of the balance. So if you start with $100, 5% of that would be $5. But then this is kind of the beginning, year zero. At the 1 year mark, they pay out the $5, they put it in your account. So now you have $105. So it sits there until you get to the end of the second year. What they do is they pay out again. They pay you 5%. But now you have $105, not $100. So that means when they pay you 5%, 5% of $105 is going to be a little bit more money because you have more money in the account. So now it's going to be $5.25, which they then deposit into your account. So now you have $110.25. So this process keeps repeating itself, but every time they pay you, they're now finding 5% of a larger number, which means every year you're going to get paid more and more and more money. So this is actually an example of an exponential relationship because the fast way to calculate a percent is to multiply. So the fastest way to find, 5% of $105 is to do 105 times 0.05, which is 5% as a decimal. So it's kind of a shortcut for calculating with percentages that hopefully you know. But we're multiplying. So since we're always multiplying by that same number, that makes this an exponential relationship. So exponential relationships show up a lot in real life. So this is an example. If you have like a savings account, then exponential relationships apply to you because your savings account earns interest exponentially. So now we're going to jump into our notes. Now that I've kind of introduced that and getting you thinking about when am I ever going to use this? So if you happen to have an account or if you ever take out a loan, so loans do the opposite. They charge you interest. So if you have a loan with 5% interest, that means every month you have to pay a fee that is 5% of however much you still owe on top of making your regular payments. So if you have or you ever will have any sort of investment account, or if you ever will take out a loan for anything, then exponential relationships apply to you because they all use that. So all of those things are using something called exponential growth and decay, which is what we're going to talk about today. So exponential growth and decay follows a basic variation of our exponential formula. So yesterday we learned that the outline for an exponential equation is y equals, and you don't have to write this down, I'm just showing you so you can see how it connects, y times b to the power of x. So you can kind of see the matching parts there. There's that part. This is the base, and then our x turned into a t. So you kind of see the pieces of the exponential function. But this has been expanded a little bit. So we have to talk about, well, what do each of those pieces mean? So if we're going to talk about something that grows exponentially or decreases exponentially, that's exponential decay. So kind of like the savings account problem I just showed you. Then we have to talk about what each of these pieces mean. So this first part, so this A, that's what's called the initial amount. So that basically is your starting amount. And the output, that's going to be your ending amount. So if we wanted to use savings problem as an example, $100 was our initial amount, and our ending amount after 2 years was $110.25. So that would be our A and our Y. So this T over here, that is the amount of time in years. So usually we measure things in years. That's kind of the default for exponential things, especially in the financial world. Everything revolves around 1 year periods of time. So that's the time. And then R, this is the rate. But the important thing is we want the rate in decimal form. What the 1 represents is the original amount. So connecting this back to the savings account problem. So the first time we got paid, we earned $5, but we had to add it on to what was already there. So the 1 basically multiplies the original amount so that you're rolling it in with what was already there. So that's all that 1 is. So these are the basic parts of kind of what an exponential formula looks like. We're going to use exponential growth or decay working with percentages. So we're going to look at a couple of examples of actually using this so you can see how does this actually work in an actual problem. So first example, 2010, the town of Flat Creek had a population of 280,000 people and a growth rate of 0.85% per year. So that means that we are growing, so growth rates. That means that this is an exponential growth. So you can see the formula has kind of a plus or minus here. So you can use a plus for something that's growing and a minus for something that's shrinking. So the very first thing we want to do is just write an equation to represent what's going on in Flat Creek. And it says since 2008. So that basically means we're going to use the 2008 population as our starting amount. So our equation, if we just drop things in, so our ending amount is going to depend upon how many years we go for. But we know our starting amount, our A, is 280,000. So we can do 280,000 times 1 plus, because this is growing. Now it says the rate in decimal form. Now this one gets tricky because it's a decimal, but it's also a percentage. So percent is out of 100. So to convert a percent to a decimal, you have to divide by 100. So the decimal form of 0.85% would actually be 0.0085. So you have to be careful with that. And then T is going to be our time. So we haven't filled a time into that yet. So this is our basic equation. So we can fill in any amount of time we want and get out the population after that amount of time. So we're literally just kind of using our outline. So we can use our equation to answer a question. What will the population of Flat Creek be in the year 2025? Well, 2008 is a starting year, so we need to figure out how many years since 2008 that would be. So 2025 is, so the fast way to find that out would be to just do 2025 minus 2008, which is 17 years. So 2025 is 17 years after 2008. So that means that the population is going to grow 0.85% 17 times. So we're going to multiply by that 17% over and over again 17 times, which is where the exponential comes from. So if we wanted to get that answer, we could drop the time in since we know it's 17 years. So to get the answer, we would do 2080 times 1 plus 0.0085 to the power of 17. And this is where, oops, I forgot the zeros there. This is where your calculator becomes your friend because you do not want to do that by hand. So your calculator does have an exponent button. So we should follow order of operations. So we should do the 1 plus 0.0085 first, which gives us 1.0085. An order of operations says we do exponents next, so we would do that to the power of 17. So this is where you can use your exponent button to help you figure out what that is. So exponent buttons look a little bit different on every calculator. So some calculators it looks like this, some calculators it looks like this, some calculators it looks like a little up arrow, like caret symbol. So you can look and see what your calculator has. But you would, if you wanted to do 1.0085 to the power of 17, you would put in your 1.0085 and then push your exponent button and then put in the 17. and then hit equals. And it gives you this big long decimal, 1.154756308044214. So we're not worried about that yet because we're not done with the problem. So we still have to multiply all of that by our 280,000. So whatever's sitting on your screen, you're just going to do that times 280,000. And now we get to the point where we can round. So try to avoid rounding until you get to the end of the problem. Because if you round in the middle of the problem and introduce a rounded number when you're not done calculating, it throws off the accuracy of your end answer. So it's okay to leave a long number sitting on your calculator screen if you're not done with it. But these exponent problems are very much calculator problems because you're not going to want to sit there and do 1.0085 times 1.0085 times 1.0085 over and over again 17 times by hand. Use your calculator to help you. That's what the tool is there for. Your job is to figure out what the correct equation is so that you're putting the right numbers into your calculator. So when this is all done, we get out, and I'm going to round because we're talking about people, so I'm going to round to the nearest person. So if you used your calculator correctly, you should get about 323,332 people. So that's our estimated 2025 population if the city keeps growing at the same rate. So that's an example of exponential growth. We also have exponential decay. So exponential decay is the same idea, but it's where something loses a percentage every year. So this next problem is an example of exponential decay so that you can have an example of both. During an economic recession, a charitable organization found that its donations dropped. So that tells you, okay, I'm losing this much by 1.1% every year. Before the recession, its donations were 390,000. So I can write an equation for that using my outline. So y equals the starting value is 390,000 times 1. And this time I'm going to do 1 minus because it's dropping by 1.1%. Again, that's the percentage. So to turn it into a decimal to use it in the equation, you have to divide it by 100. So 0.001 or sorry about that. I got an extra 0 in there on accident. So 1.011%. So 1.1 divided by 100 to turn into a decimal, 1.011%. And then however long we go for. So if we wanted to find where it's going to be out after 5 years of decreasing donations, then we can drop a 5 into our equation and we can do 390,000 times 1 minus 0.01 to the power of 5. And again, this is where it is fully okay to use your calculator to help you once you've figured out the equation. So we need to use order of operations. So let's do the parentheses first. So 1 minus 0.011, I lost a 1 there, sorry, equals 0.989. And then we're going to do that to the power of 5 because exponents come next. And then we're going to multiply times 390,000. So calculator used correctly, that should give you about, and now we're talking about an amount of money, so we're going to label our units. So 369,016 in money, the farthest we could go is to the nearest cent. So if you didn't do any rounding on your calculator to the end, and you round it off, you'd get $369,016.74 would be how much they're getting in donations 5 years into the recession. So that's the basic idea of how we can use an exponential equation to help with exponential growth and exponential decay, which are real life situations involving percentages. Real life situations involving percentages are typically exponential because we multiply when we calculate percentages, and that creates a multiplying relationship, which is what exponential is. One last thought on this. So there is an application of exponential growth. So if you look at this formula right here, this looks like the exponential growth formula with some extra stuff added in because it is. So one application of exponential growth, while we're talking about exponential growth, is something called compound interest. So back to that savings account problem that I introduced at the beginning of the lesson to show you exponents in real life. In the financial world, percentages are calculated yearly. So you probably heard of something called an APR. So maybe you might hear that, an investment has a certain APR or a credit card has a certain APR. So APR stands for annual percentage rate. And that basically means if that were to pay out, or if you were only to be charged once a year, that's the percentage that you would either make or that you would have to pay. So parts of this work a lot like our regular exponential growth. So P is what's called the principal, or the starting amount. So that's the same as our regular exponential growth formula. We just changed the variable. So A is still our ending amount, just the same as exponential growth formula. So what changes is that now we've got some division happening here and some multiplying. So we introduced this N in there. So N is the number of payouts in a year. So let's say you had something and it has an annual percentage rate, but it does something called compounding monthly. That basically means it pays you monthly. So whatever percentage rate that is, you're going to get 1/12 of that percentage rate every month. So say if you had a 5% payout for the year, you're going to get 1/12 of that 5% payout every month, which is why when we calculate the percentage, we have to divide it by the number of payments to show us basically how much are we getting each time. And then since what's up here normally works off of a 1-year span, if you're getting paid more frequently than a year, then you're going to get more payments in a year. So if you're getting paid monthly, then your exponent would actually need to be a 12 in order to calculate what happens at the end of the year, because you're going to get paid 12 times in the year. Because remember, we said that that exponent is usually tracked in relative to years. So if you're getting more payments, then you're going to have to multiply more times to get to that 1-year mark. So it basically is our exponential growth formula, just adjusted for the fact that in the financial world, you might pay or have to make payments more frequently than once a year. So this is an example. When June was born, her grandparents invested $1,000 in a fixed rate savings account at a rate of 7% compounded annually. So this means that she is getting paid. So annually means once per year. Which is going to make this problem a little bit easier. June will receive the money when she turns 18 to help with her college expenses. So we want to figure out how much money is she going to get on her 18th birthday. So what we're going to do is we're going to drop this all into our compound interest formula, which is really our exponential growth formula. So our starting amount is $1,000. 1 plus, so the interest rate again is a decimal is 7%. 0.07, and this time it's just getting divided by 1 because we're only getting paid once a year. But if we were getting paid more often than that, then we would have to divide it. It's power of, we're going to get 1, so we're going to get 18 payouts because it only pays once a year. So 1 payout per year times 18 years worth of payouts. So that is what we're going to use to calculate our answer. So we can clean this up a little bit because we're dividing by 1 here and we're multiplying by 1 here. So we're going to get 1,000 times 1 plus 0.07 to the power of 18. And now this is a grab your calculator problem again. So 1.07 to the power of 18, and then multiply it by 1,000. So that means that on her 18th birthday, if you round off your final answer, we're talking about money, so label the units. If you drop this in your calculator correctly, June is going to get $3,379.93. So not a huge amount of money, but still, her investment tripled just sitting there, and that's not a bad thing. So there you go. That is exponential growth and exponential decay, and compound interest, which is really also exponential growth. So what you're going to do today is you are going to practice doing some problems like this that are going to use our exponential growth and exponential decay formulas so that you can practice calculating with exponential formulas for real life situations.